The sky appears vast and empty. From the ground, it seems aircraft can roam freely. This is a common misconception. In reality, the airspace above us is highly structured. It is a complex network of invisible highways. These highways have rules, just like roads on the ground. One of the most critical sets of rules governs vertical space. This ensures aircraft maintain safe distances from one another. This order is essential for preventing mid-air collisions. Think of it as a multi-story building, infinitely tall. Each floor represents a specific height. Aircraft are assigned to these different floors. This keeps them safely separated vertically. Pilots and air traffic controllers work together. They meticulously manage these vertical assignments. Without this system, air travel would be chaotic. It would be unthinkably dangerous. The order above is a silent guardian of safety. This system of vertical separation is not arbitrary. It is based on well-defined principles and procedures. These are known as flight level allocation rules. Join me as we navigate the vertical dimensions of flight. What exactly is a flight level? It sounds like altitude, and it is related, but there's a crucial difference. Altitude is height above mean sea level. This is measured using the local atmospheric pressure. This local pressure changes with weather. It also changes from place to place, so true altitude readings can vary. This variation can be a problem for aircraft separation. To solve this, the concept of flight levels was introduced. A flight level is a standard pressure altitude. Aircraft altimeters can be set to a standard pressure. This standard is 1013.25 hectopascals, or, in North America, 29.92 inches of mercury. When an altimeter is set to this standard, it reads flight levels. Flight level 350 means 35,000 feet on this standard setting. This creates a common reference for all aircraft, ensuring everyone is using the same ruler. Using a standard setting simplifies things greatly. This uniformity is critical for safety. One of the most common systems is the semicircular rule. This rule dictates appropriate flight levels. It is based on the aircraft's magnetic track. The magnetic track is the actual path over the ground, not necessarily the aircraft's magnetic heading. Wind can cause a difference between heading and track. The rule divides flight paths into two main categories: eastbound tracks and westbound tracks. This simple division helps organize traffic flow. For instrument flight rules flights, aircraft on magnetic tracks from 0 degrees to 179 degrees are eastbound. These eastbound flights use odd thousands flight levels. For example, flight level 210, flight level 230, flight level 250, and so on. Aircraft on magnetic tracks from 180 degrees to 359 degrees are westbound. These westbound flights use even thousands flight levels. For example, flight level 220, flight level 240, flight level 260, and so on. This creates a 1,000-foot vertical separation between aircraft flying in roughly opposite directions. The rule provides a basic layer of protection. If two aircraft are on reciprocal tracks, they should be separated. One would be at an odd level, the other at an even level. This inherently provides 1,000 feet of vertical space. Before the semicircular rule, there was the quadrantal rule. It is still used in some regions, notably the UK. The quadrantal rule divides tracks into 4 quadrants. Instead of 2 halves, like the semicircular rule, it was based on the aircraft's magnetic track. This provided more granular altitude assignments. The quadrantal rule was more common for VFR flights. It often involved adding 500 feet to IFR levels. This provided separation between IFR and VFR traffic. Section 5, Transition, where altitude becomes flight level. Transition altitude is crucial. Below it, aircraft use local altimeter settings called QNH. QNH gives altitude above mean sea level. Above transition altitude, pilots switch to flight levels. They set altimeters to 1013.25 HPA. The transition level is the lowest flight level. It must be above the transition altitude. The USA has a fixed transition altitude of 18,000 feet. Aircraft switch to standard pressure at this altitude. Section 6, Global Skyways. A patchwork of vertical rules. The world of aviation is global. Aircraft frequently fly across international borders. However, flight level allocation rules are not universally identical. While ICAO provides standards, regional variations exist. The semicircular rule is widely adopted, especially for IFR en route. This provides a good degree of international harmonization. Most of the world uses east odd, west even for IFR. This is for flights above the transition altitude or level. This consistency simplifies international flight operations significantly, however differences can be found. One significant area of variation is reduced vertical separation minima, or RVSM. In RVSM airspace, typically between flight level 290 and flight level 410 inclusive, aircraft can be separated by only 1,000 feet vertically. Previously 2,000 feet was required at these high altitudes. RVSM requires specific aircraft equipment and crew training. While RVSM itself is a standard, its implementation details might vary, or the specific flight levels covered by it. The metric system for flight levels is another variation. Some countries like China and Russia use metric flight levels. Instead of feet, altitudes are expressed in meters. For example, flight level 8,100 meters, which is about flight level 266. Section 7, ATC's Watchful Eye, Managing the Vertical Realm. Flight level allocation rules provide a fundamental framework. They establish a baseline for vertical separation. However, air traffic control, or ATC, plays an active, vital role. Controllers are the conductors of this complex aerial orchestra. They assign flight levels to aircraft. They monitor aircraft to ensure they maintain their assigned levels and intervene if any deviations occur. Their job is to ensure safe, orderly, and expeditious flow of traffic. Rules alone are not enough. Human oversight is key. ATC uses radar and other surveillance technologies. These tools display aircraft positions, altitudes and speeds. Controllers can see if an aircraft is not at its cleared flight level or if it's climbing or descending without authorization. They provide tactical separation, sometimes deviating from standard rules. For example, to resolve a potential conflict or to accommodate weather deviations or operational needs. They might instruct a flight to maintain a non-standard level temporarily. This is always done with safety as the top priority. Controllers also manage the transition between altitude and flight levels. They provide aircraft with the correct local QNH. Section 8, Altitude Amnesia Common Blunders and How to Avoid Them. Despite clear rules and ATC oversight, errors can occur. Altitude deviations or level busts are serious safety concerns. They can lead to a loss of separation with other aircraft. Understanding common mistakes helps in preventing them. One frequent error is incorrect altimeter setting, forgetting to switch from QNH to standard at transition altitude, or setting the wrong QNH value when descending. This can result in the aircraft not being at its intended true height, leading to a discrepancy with what ATC expects. Misunderstanding or mishearing ATC clearances is another pitfall. A pilot might mistake flight level 230 for 250. Read back and hear back procedures are crucial here. Pilots must read back the clearance exactly as heard. Controllers must listen carefully to confirm it's correct. Fatigue, distraction, or high workload can contribute to these errors. Complacency can also be a factor, especially on familiar routes, assuming a standard clearance without full attention. Section 9, Conclusion, Vertical Separation, the bedrock of air safety. The allocation of flight levels is not just a technical detail, it is a cornerstone of modern aviation safety. The semicircular and quadrantal rules, though simple in concept, provide a systematic way to organize air traffic vertically. They are the first line of defense against mid-air collisions, ensuring that aircraft on different tracks have inherent separation. This fundamental principle has saved countless lives, and it allows for the high volume of air traffic we see today. Without it, our skies would be far more dangerous. Understanding these rules is not optional. For student pilots, it's a building block of safe flying habits. For flight dispatchers, it's integral to planning safe routes. For air traffic controllers, it's a tool for managing the sky. The transition between local altimeter settings and standard pressure is a critical procedure that demands precision and attention. Regional variations require constant awareness and adaptation. The global aviation system relies on this shared understanding and consistent application of these vertical separation minima. Common mistakes, often rooted in human factors, highlight the need for continuous training and vigilance. Robust standard operating procedures and clear communication are essential to mitigate the risks of altitude deviations.